Ice melting reorganizes molecules into a liquid state, but leaves the atomic bonds intact. Burning paper alters the molecular structure entirely, destroying the carbon lattice to produce carbon dioxide and water vapor. We confirm this structural alteration occurred through macroscopic evidence, sudden shifts in color or rapid spikes and drops in temperature. Other reactions announce themselves by evolving gases into the air, or by instantly generating dense, insoluble solid matter out of completely clear liquids. Early chemists had no tools to see the atomic scale. They relied entirely on observing these visible, macro-level phenomena in the laboratory to infer the invisible mechanics occurring below. Descriptive observation provides the qualitative foundation, but to gain predictive power over matter, we must translate these macroscopic events into rigorous mathematical models. The foundation of this mathematical translation is the law of conservation of mass. In a closed system, atomic matter is never created and never destroyed. It is only infinitely rearranged. This physical constraint dictates how we construct written chemical equations. We must perfectly account for every atom that enters and exits the reaction through the practice of stoichiometric balancing. An unbalanced equation describes an impossible physical scenario, one where matter spontaneously appears from the ether or vanishes without a trace. Stoichiometric balancing acts as a mandatory reflection of physical reality. Every written model must obey the arithmetic of conservation. Consider the interaction between solid iron and gaseous water. The resulting products are magnetite and hydrogen gas. Counting individual atoms on both sides iteratively, the tabular method, is slow and highly prone to error when processing complex compounds. We replace guesswork with the algebraic method, assigning a mathematical variable to each molecular coefficient. For the iron atoms to balance, the quantity on the left, A, must equal 3 times the quantity on the right, C. The hydrogen atoms require their own linear equation. 2 times B must equal 2 times D. And the oxygen atoms provide the final constraint. B equals 4 times C. By setting the highest frequency variable, C, to 1, we systematically solve for the remaining variables, giving us exact whole number coefficients, 3, 4, 1, and 4. Algebraic resolution ensures that predicting exact chemical product ratios is a deterministic mathematical certainty. Once balanced, these equations reveal specific architectural archetypes. In a combination reaction, multiple simple reactants fuse to construct a single, highly structured product. This fusion is driven by an exothermic process. The formation of new, stable bonds aggressively releases heat energy into the environment, an atomic-level event that scales up to generate massive industrial power. The architectural and thermodynamic inverse is the decomposition reaction, where a singular compound fractures into discrete pieces. Applying intense thermal energy to green ferrous sulfate crystals forces the molecular lattice to break apart, violently expelling trapped water molecules. This microscopic fracturing manifests macroscopically. The green crystals bleach white, and upon further heating, degrade into reddish-brown ferric oxide. As the solid fractures, it simultaneously generates highly acidic byproduct gases, specifically sulfur dioxide and sulfur trioxide. Extreme heat provides the precise thermodynamic trigger necessary to break a stable molecular equilibrium and force sudden decomposition. Heat is not the only mechanism for cleavage. Electrolytic decomposition forces molecular separation using a continuous electrical current. This schematic details the electrolysis of water. The current splits the H2O molecules, collecting hydrogen gas at the cathode and oxygen gas at the anode. The balanced equation dictates a strict 2-to-1 volume ratio for the resulting gases. Energy input takes the form of direct photon exposure in a process called photolytic decomposition. Exposing white silver chloride to direct sunlight breaks its bonds. The chlorine evaporates as a gas, leaving behind a residue of solid gray silver. This specific photolytic decay, capturing an image by selectively exposing silver halide compounds to light, provided the chemical foundation for early black and white photography. Breaking strong chemical bonds strictly requires a targeted, quantifiable injection of energy, whether derived from a flame, an electrical circuit, or photons from the sun. When different elemental compounds interact, the reaction takes the form of single displacement. an aggressive atomic swap, where one element forces another out of a pre-existing compound. This gradient details the reactivity series, a strict empirical hierarchy ranking elements from highest electrochemical dominance at the top to lowest at the bottom. When solid iron is placed into aqueous copper sulfate, iron's higher position on the gradient mathematically validates its ability to displace the copper ion. We observe this transfer macroscopically as the deep blue copper sulfate solution degrades into a light green iron sulfate. The inverse scenario yields zero reaction. Placing solid copper into iron sulfate does nothing because copper lacks the electrochemical potential to force iron out of solution. Chemical displacement is a rigid, predictable function, dictated entirely by a metal's innate ranking on the electrochemical gradient. Double displacement reactions involve a mutual, simultaneous exchange of ions between two distinct aqueous compounds. Consider the laboratory combination of two completely clear liquids, lead nitrate and potassium iodide. Upon mixing, the ions break their initial bonds and seamlessly swap structural partners, resulting in potassium nitrate and lead iodide. The newly formed lead iodide is a precipitate. It forms a thermodynamically insoluble solid that instantly separates from the surrounding aqueous environment into a highly ordered matrix. The clear solutions instantly transform, yielding a dense, opaque yellow solid that serves as the definitive proof of this double displacement. By combining soluble liquids to generate an insoluble solid, double displacement reactions force a massive physical state change dictated entirely by the limits of chemical solubility. Tracking the gain or loss of oxygen serves as a proxy for the actual, invisible mechanism of chemical exchange, the transfer of electrons. We formally define oxidation as the total loss of electrons from an atom and reduction as the corresponding gain of electrons. These forces share an unbreakable symmetry. Oxidation and reduction cannot occur in isolation. They execute simultaneously as a paired redox reaction. An oxidizing agent is the chemical species that accepts electrons, meaning it is reduced as it forces the oxidation of its counterpart. A chemical reaction operates as a perfect zero-sum economy of electrons, ensuring every microscopic exchange is mathematically accounted for. A fully balanced chemical equation is a high-density information matrix. It encodes the exact stoichiometric mass ratios, dictates the thermodynamic state, and identifies its structural typology, such as single displacement. Below that, it tracks the deepest layer of invisible data, the simultaneous flow of the underlying electron economy. The macroscopic phenomena of heat, color, and physical phase shifts are the chaotic byproducts of a strictly ordered, perfectly balanced, and mathematically verifiable atomic reality.